So problem 1 covers 4B, 4C, 5B, 5A, and 7D. So 4B and 4C are the transient heat conductions or transient heat transfer in 1D and 2D, and it's in 2D, so therefore it covers 1D. It's both cylindrical and with a plane wall. It's 5B because it is cylindrical coordinates, with it being a log, and then 5A is Cartesian coordinates, and that's the plane wall being part of the transient heat transfer as well. For 7D, it is the phase change concept because in the part B of this problem, it asks about some condensing on a wall behind the stove. Then as for problem D, it covers learning outcome AB as it is a unit operation for mass transfer as it's filtering ammonia out of air and it's a simple membrane problem. As for problem 3, it covers 2A and 2B, which is the deriving and solving of the conduction equation, and that is because it is modeling a vat of wax as a body to model heat transfer in. And then it also covers 5A because it is Cartesian coordinates as it's one-dimensional heat transfer, and that it's not cylindrical and spherical. And then it is also 8A because in the last part of the problem, it asks how to take the temperature down to the necessary needs to start making candles. As for problem 4, it covers concepts 5C and 6A, 5C being at spherical coordinates as it is mass transfer out of a spherical shell, and then 6A because it is transient mass transfer. And then as for the last problem, it is just simply 6B. This is the bowl being treated as a semi-infinite solid and measuring a concentration at a certain depth within the bowl, and that's all calculated with this problem, and so therefore it is transient mass transfer. So for problem 1, our goal is to find how long it will take for an internal temperature of 56 degrees Celsius, and so we can assume that there's not going to be any heat loss due to nucleation on the wood. The pot is going to have a uniform temperature, thermal properties are going to stay constant for the wood, there's going to be no mass transfer into the wood, and Q-rad can be negligible. So we're given the dimensions of the wood, and we're given the temperatures, and we have our goal temperature right here at the location in the wood as well. So we get all these properties. K wood in the cylinder direction, so in the radial direction, basically cross grain is going to be this, and the other direction is this, and then we have the CP for the wood and the density of the wood as well, and we have all the properties for the liquid. So using all that, we can find a Rayleigh number. Using that Rayleigh number, we can get the Nusselt number, and then using the Nusselt number, we can get the heat convection coefficient. And that's exactly what we do down here, and we use that heat convection coefficient to get the BO number, using both of the thermal conductivities for the respective BOs, and then we get these lambdas and A's. Using those lambdas and A's, we can get the thetas, and because it's at the center, we have the simplified version right here, and because it's combined 2D heat transfer, it's going to be the product of these two thetas, going to be the total theta, and so we get this expression for T, and T being a total of 79 hours. And this is very high, but it makes sense because we are neglecting mass transfer into the wood as well as the thermal conductivity increase by the increase in water. So then for part B of the problem, we are looking at how the rate of condensation on the wall behind the stove. And so first, we have the surface of the wall is 20 degrees Celsius, and then the bulk property temperature is 100 degrees Celsius, which comes from the Tsat from the pressure given. And then the arithmetic average is used to draw the temperatures, which is going to be the T film, and we get all these properties. We can plug in all these properties to this equation, but also first getting the H star FG, and then that through this equation. And once we get the H, we can then plug it into the Q equals HAS, the Newton's law of cooling. And so from that, we can get the total rate of condensation from this Q dot divided by the HFG is going to give us this rate of condensation. So then for problem 2, we are tasked with finding the necessary permeant to achieve the outcomes that we want out of this filter. And so we have the pressures on the inside and outside, or the permeant and retentate, and then we have the input composition, and we have the output composition as well, or the output recovery. And so using that, we can find the total molar flow rate, and using this expression, we know the surface area, and we can calculate the delta P log mean of the partial pressure of the ammonia, and we find the delta P log mean, and we plug it into this equation, which is the total molar flow rate divided by the surface area times the delta P log mean, and we get a necessary permeance of 2.254 moles per meter squared seconds kPa. And this is relatively low because there's such a high pressure on the inside and such a low pressure on the permeate side. So then for problem 3, we're tasked with deriving an expression for the heat conduction and then solving that expression. And so we can assume that it's going to be 1D heat transfer, it's going to be steady state, and that the thermal properties are going to be constant. It's known that we need at least 50 degrees Celsius, so the T surface is going to be 50 degrees Celsius, and the heating is only coming from the bottom. So in order to get our expression, we start with a energy balance, which is the conduction through an element minus the conduction out of the element, plus the generation is going to equal the total change in energy, and we get this expression right here. And as we take the limit of delta x and delta t going to 0, we can get this expression right here, which is the expression we usually see for 1D heat conduction. And then we get this final expression right here. Using the boundary conditions that the convection is going to equal the conduction and the negative conduction right here, this is what we get for C1 to plug back into the Tx, and then we can solve for Tx, which is a total going to be this expression down here where Tx is negative 1200x plus 50 degrees Celsius plus 1200. And it gives us this expression right here. And this is evident that it's not very smart to store 1 meter's worth of thick wax, like hot wax, because at the heating surface it needs to be 1200 degrees in order to keep that melted temperature. And so either have a shallower bath or keep the wax solid. Then the second part of problem 3, we're tasked with designing a heat exchanger to bring the temperature down to a reasonable temperature to start making candles. And so we do the delta T log mean temperature difference, and we can find that by doing the inlet and outlet temperatures with delta T log mean. But then we have the F is also equal to 1 for the geometry, and this U naught is going to be the inverse of all the resistance added up plus the fouling factor, which I add in down here. And so we get the U naught is this 39.695, and we get an expression for the surface area being Q dot divided by the U times delta T log mean. And that Q dot is actually the what we got out of the heat exchanger from the in and outlet of the wax, because we know those temperatures and we know the specific heat as well. We get that Q, and so we get this total meter squared. And this makes sense just because the low thermal conductivity of the wax, and also this could be corrected by just having a multiple pass heat exchanger. That does lower the F, however, it does increase surface area, so it does make up for it. So then for problem 4, we have to find the total molar flow rate out of this Orbi, and so we assume that's going to be a steady state mass diffusion, and also that the diffusivity is going to be constant because the temperature is going to be constant. And we find that the property for the diffusivity of water in this polymer is actually this right here. And through the book, we find this equation for 14-28, where the total molar diffusion is this expression right here. And so just plug in the values given in the problem and keep everything in the same units, so centimeters squared, and converting this to centimeters cubed from liters, and we get that the total molar flow rate per second is 1.1677 times 10 to the negative 10th. Then lastly, we do the problem where we treat the bowl as a semi-infinite solid for transient mass transfer, and we know that the infinity or the bulk molarity is 5 molar, and the initial molarity is 0, and then we want a molarity of 0.2 at 1 centimeter deep. And so this is a rough concentration profile that you may see, but basically we're going to treat the bowl as a semi-infinite solid, just like a plain wall, because it's such a small boundary layer that it can be treated like that. And so we get this equation similar to the theta in heat conduction, and we just solve. We find that this is going to be 0.04, and using the tables we can back out an argument for the error function of this, and then plug that back in to this to solve for the total T, and it turns out to be 13.05 days, and that makes sense just because of how small this diffusivity is.